Hi, welcome to this lesson on logistic regression. In the previous lesson, you learned about the multiple regression model. You've learned how multiple predictors can be used to predict one continuous dependent variable. But what if your dependent variable isn't continuous but binary? For that, you will use the logistic regression, which is the topic of this lesson. Let's get started. Logistic regression may not be the most common form of regression, but they are very, very useful. Logistic regressions are very similar to their linear counterparts in terms of use and interpretation, and the only real difference here is in the type of dependent variable they use. In a linear regression, the dependent variable is a continuous variable. In a logistic regression, the dependent variable is a binary, a subgroup of the dichotomous variable, meaning that the variable can only have two possible values. Because of this, when interpreting the binary logistic regression, we are no longer talking about how our independent variables predict a score, but how they predict which of the two groups of the binary dependent variable people end up falling into. For instance, this can be fail or success, or people who didn't leave the company and people who did leave the company. To do this, we look at the odds ratio, which is often confused with probability. Probability of success is the number of successes divided by the total number of trials. The odds of success is the number of successes divided by the number of failures. For instance, you have a probability for success of 25%. That means that in 4 trials, you have 1 success and 3 failures. Therefore, your odds ratio is 1 divided by 3, which is 0.33. However, if you have a 50% chance for success, you have an odds ratio of 1, as 1 divided by 1 equals 1. The higher the odds ratio, the higher your chances of success. You can always turn an odds number into a probability number and vice versa. We use the odds ratio instead of the probability because the odds ratio has some advantages in statistics. For example, in logistic regression, the odds ratio represents the constant effect of a predictor X on the likelihood that one outcome will occur. The key phrase here is constant effect. In regression models, we often want to measure up the unique effect of each x on y. If we try to express the effect of x on the likelihood of a categorical y having a specific value through probability, the effect is not constant. What that means is that there is no way to express in one number how x affects y in terms of probability. The effect of x on the probability of y has different values depending on the value of x, which means that it is not a linear relationship like in the linear regression. The difference between a linear regression and a logistic regression can be seen in this picture. A logistic regression produces a logistics curve, which is limited to values between 0 and 1, as the dependent variable is a probability variable between 0 and 1. Depending on the value and relationship of the independent variables, the probability of success, or 1, increases or decreases. Logistic regression is similar to linear regression, but the curve is constructed using the natural logarithm of the odds of the target variable. Moreover, the predictors do not have to be normally distributed or have equal variance in each group. As you can see, the higher your score, the higher your odds will be for the predicted variable. In logistic regression, the constant, b0, moves the curve left and right, and the slope, b1, defines the steepness of the curve. By simple transformation, the logistic regression equation can be written in terms of an odds ratio like this. Finally, taking the natural log of both sides, we can write the equation in terms of log odds, logit, which is a linear function of the predictors. The coefficient, b1, is the amount the logit, or log odds, changes with 1 unit change in x. In Module 2, I used the example of a turnover test that would predict if someone would leave the company on a dichotomous scale, yes or no. The threshold for this imaginary test was 15. If all the variables combined would create a score above 15, we would say that the test would give a positive result, stating that the person will most likely leave in the next year. If the score was below 15, the test would give back a negative result, saying that the person wouldn't leave. This example was an example of a logistic regression. The higher the score, the higher the odds were that the person would leave. With this information, we can visualize our turnover example. Here, you can see the x-axis has the combined predictor value, where if you score above 15, you have a 50% chance of leaving the company within the next year. We felt that this threshold was sufficient. As you can see, the data we've gathered can either be at the bottom or at the top, either 0 or 1, not leaving or leaving. The curve presented is defined as the odds of success, which in this case is ironically leaving, aka a successful prediction that someone has left. The more you are to the left of the slope, the less likely it is that you will leave the company according to this model. However, our model isn't perfect, as you can see multiple data points where we didn't expect the person to leave when they did in fact leave. We can change this cutoff point of 15 to wherever we like, depending on our need for the test. To understand which cutoff point would give us the most accurate model, we can use a ROC curve with our logistic regression. When you do a logistic regression, you are given two classes coded as 1 and 0. In our case, this is turnover, left the company or did not leave the company. With the logistic regression, we can now compute probabilities that given some explanatory variables, an individual belongs to the class coded as 1. If you now choose a probability threshold and classify all individuals with a probability greater than this threshold as class 1 and below as 0, you will, in most cases, make some errors because two groups cannot be discriminated perfectly. For this threshold, you can now compute your errors and the so-called sensitivity and specificity. If you do this for many thresholds, you can construct a ROC curve by plotting sensitivity against 1 minus specificity for many possible thresholds. ROC stands for Receiver Operating Characteristic. Due to the fact that our model has true positives, true negatives, and false positives, we can also make a confusion matrix, which is the matrix that illustrates how many of each of these occur in our model. The next example shows both the ROC and confusion matrix in action. With the ROC curve, you can see that if we take a lower threshold, we will increase our true positive rates, but also increase our false positive rate. Lowering your test threshold to classify someone as 1 makes it so that you correctly identify more people as wanting to leave, but also classify more people incorrectly that they want to leave, even though they won't leave in the next year. Likewise, if we increase our threshold, we will decrease our true positive rate and decrease our false positive rate. The confusion matrix is the same matrix we used in Module 2 to describe true positives and true negatives. The top left has the amount of true positives, top right is the amount of false positives, bottom right is the amount of true negatives, and bottom left is the amount of false negatives. Combined, you can now see how your logistic regression model performs with real numbers, rather than on an abstract level. For a step-by-step guide for doing logistic regression in different statistical programs, we will refer to the reading material. Finally, let's take a look at the assumptions for our logistical regression analysis. First, logistic regression requires that the dependent variable to be binary. Second, logistic regression requires the observations to be independent of each other. In other words, the observation should not come from repeated measurements or matched data. Third, logistic regression requires there to be little or no multicollinearity among the independent variables. This means that the independent variables should not be too highly correlated with each other. Fourth, logistic regression assumes linearity of independent variables and log odds. Although this analysis does not require the dependent and independent variables to be related linearly, it requires that the independent variables are linear related to the log odds. So that's it for this lesson. In this lesson, you learned about the logistic regression. Specifically, you learned when it's used, what the differences are between the logistic regression and the multiple linear regression, and the assumptions for the logistic regression. In the next lesson, you will learn about structural equation modeling, which is your first step in understanding how machine learning works with regards to statistics. See you there.